So, hello everyone. So today we'll start our first class on fundamental of statistical thermodynamics. So, so in this class we'll be basically first class we will be basically discussing about the introduction part. Okay, and we will also try to solve some of the problems on that particular discussion. So first we just discuss briefly about the things that are in the theories that are needed to solve the problems, the concepts. So let's start. So introduction. Week 1. So first let's us consider a closed system with n numbers of molecules. Okay, so a closed system with n numbers of molecules. So this n numbers of molecules is fixed. Okay, so the n is constant here. And let's suppose the total energy of the whole system, total energy of the system is equal to E. So in a system, the system is described by two quantities. That means one is the number of molecules and the total energy of, governed by the system. Okay. So now our fundamental question is that how this total energy E has been distributed with this n numbers of molecules. Okay. So the thing is like that. So let's suppose this there inside the system there are many energy levels, right? Like E1, E2, E3, like this up to En. Okay. And our primary goal of this discussion would be, initial part of this discussion would be to find out what is the way the particles, number of particles that has been distributed throughout this energy level. Okay. So let's suppose in the E1 energy level, N1 numbers of particles are there, E2 energy level, N2 numbers of particles, N3 numbers of particles. So likewise, they will follow some kind of a distribution, right? Uh, which basically guided them to level up into the energy levels. Okay. So yeah, so this is our main goal. So we want to find out the description of the distribution of energy on on the energy levels. Basically, that means you want to calculate the population in each energy level. Okay. And for that, we will consider that the population state for any type of molecules in any mode of motion at any temperature. Okay. So we will consider that uh, population of any type of molecule in any mode of motion at any temperature. These are the things we'll consider. And also there we have to also apply to restriction into the system also. One restriction is the first one is the molecule should be independent. So the motion of each molecule cannot uh, affect the motion of other molecules. Okay, so distribution is like independent. Okay, distribution of each and every molecule uh, has been calculated in a such a way that the molecule should be independent. Okay, molecules should be independent. Second is sum of total energy of the system is sum of individual energy. Sorry, the total energy, not sum of. The total energy of the system. Total energy is basically sum of individual energy of the system. Okay. These are the two restrictions. Okay. And for the time being, you are neglecting the complicated interaction that is happening in the molecule. So that interaction energy for the time being you are not considering. Okay. So that we have to also write. So we discarded the contribution of the interaction energy happens in the total energy of the system. Okay. So this is the way. Okay. So these are the few things that we have to keep in our mind to do all the calculations to derive basically the distributions. So so next thing. So now we jump into the algebra. So before that, uh, let me discuss some general concept on distribution, probability distribution basically. So, so as you have discussed, so the particles are basically distributed in like this way, right? So let's suppose this is the zeroth level E0, this is the first level E1, E2, like this. There are so many levels are there. So each level, there are, let's suppose, N0 numbers of molecules in A0 level, N1 numbers of molecule E1, N2 numbers of molecule E2. So that means the total number of molecules, that is N, is basically N0 plus N1 plus N2, like this, right? So, so that means this N0, N1, N2, there are a certain numbers of uh, the different ways by which this number of molecules can be distributed in this energy level, right? And these different ways are basically known as the weight of the configuration. Okay. So this W is like different ways general configuration can be achieved. So, so this W is known as the weight of the configuration. Weight of the configuration when 0 and 1, like this. Okay. This is known as the weight of the configuration. So the expression of W would be looks like this. W would be n factorial by n0 factorial, n1 factorial, n2 factorial, like this. So this is the number of total number of ways of this n0, n1, n2 molecules can be distributed in the corresponding energy levels. Okay. Let me give you an example. Let's suppose there are 20 particles are there, and out of this 20 particles, let's suppose the particles are distributed like this. So energy 0, E0 has let's say 1 particle, energy E1 has 10 particles, 5 particles, 3 particles, 0 particles, and 1 particle. So like this, let's suppose the 20 particles are distributed inside the energy level. So the number of possible ways this distribution can happen, so that particular value is then W is equal to 20 factorial divided by 1 factorial, 0 factorial, 3 factorial, 5 factorial, 10 factorial, 1 factorial. So it would be 9.31. If you calculate it, would be 10 to the power 8. This is the possible number of ways by which these particles can be distributed in this particular sequence, in this particular configuration. Okay. So yeah. So now, so let's do an example problem on regarding this. Okay. So let's try to figure out the problem. So the first problem is problem number 1. Let's suppose 4 distinguishable so let's suppose there are 4 distinguishable coins are there. Okay. And these coins are tossed in a large number. Then then write down the different microstates which may be observed and the macrostates into which they would fall. Okay. So basically the problem is like that there are four distinguishable points, so they are being tossed. So yeah, so okay. So they are distinguishable points. So microstates are basically giving you the macro state is basically the configuration, the type of configuration you can get. That is basically called the macro state in the system, and micro state is the possible ways that by which we can get that particular configuration. Okay, so this is basically given by the micro state of that particular macro state. Okay, so let's solve the problem, then it will be clear. So let's basically so these four are basically distinguishable points, right? Let denote those 4 points as like A, B, C, D. Okay. So let's first write macro state in this column, micro states in this column. Number of microstates corresponding to each macro state and probability of each macro state. Okay. So first macro state would be number of heads. So if you toss 4 coins, let's one case should be like this where all the 4 points can be show you head. Okay, so number of head is 4 and number of tail is 0. So all of the points is showing you heads. Okay, so in that case the possible microstate is that all A, B, C, D. So head, microstate, let's suppose head and tail. So that means all these points A, B, C, D, all these 4 points will get in the head state, right? A, B, C, D. Okay. And no other coin is going to be in tail state. No other coin has the tail, right? Tail up. So number of coin that has been tail up is equal to 0. So that means total number of microstate is just 1. This only for this particular configuration only one microstate is possible. That is all the coins are in head state. So A, B, C, D. So the probability would be, so the total probability we know there is 4 coins. So total number of different configuration can you get is 4 factorial. That is sorry, 2 to the power 4. 2 to the power 4 is the total number of configuration. So that gives you 16. So it should be 1 by 16. Okay. Next case where what can happen? Let's suppose macro state is like that, the configuration is like that. 3 coins are showing head and 1 coin is showing tail. Okay. And the number of possible combination that can happen for this particular configuration is that, let's suppose A, B, C showing head and D showing tail. Or it can happen like this: B, C, D showing head and A is showing tail, C, D, A is showing head and B is showing tail, D, A, B is showing head and C is showing tail, right? So These are the possible combination that can occur for this particular configuration. So that means the total number of microstates or total number of weight for this particular configuration is equal to 4. And the probability of this particular configuration would be 4 by 60. Okay. Similarly, the opposite also yeah. Similarly, this also can happen in head has 2, in tail has 3. So in that case, it would be AB is having head, CD is having tail. Similarly, AC is having head, BD is having tail, BC is having head, AD is having tail, AD is having head, BC is having tail, BD is having head, AC is having tail, or CG is having head, AB is having tail. So these are like different configuration, different combination that can happen for this configuration. So for this case, we are having the highest number of weight, that is 6. The probability is 6 by 60. Okay. So in this way, for this particular problem, you can calculate the different ways. Okay. The next combination would be like this. In head would be 1 and in tail would be 4, right? Sorry, this would be 2, 2. Sorry, this would be 3. Yeah. Net would be in head would be 1 and in tail would be 3, right? So the opposite of this. So here it would be like 3 A B C B, A B C D B C D A and C D A. Similar here, the configuration is total number of weight is 4. It will be 4 by 16, and the last would be where all of them are tail. Nt is equal to 4 and n number of weight equal to 0. So here it would be 0. It would be A B C D. Its configuration now weight is 1, so probability is 1 by 16. So these are like the different configuration. So first, so we have discussed the system consists 4 distinguishable points. So our goal is to find out different configuration. So each coin can have either head or tail. So based upon that, we consider different configuration, where some cases there would be can be 4 head 0 tail, or 3 head 1 tail, or 3 tail 1 head. So different configuration we have considered, and under each of the configuration we have calculated the weight of that particular configuration. And you have also calculated the probability of each of this configuration, and we have find out that in this case, where number of head is equal to 2 and number of tail is equal to 2, we have the highest number of weight, and the probability is also higher for that particular. That it should be right. In the ideal case, there should be 2 head and 2 tail if you toss 4 points, right? So yeah. Similar type of problem can also be done in a science using a science example. Okay. So let's take now particles. Okay. Not any points around. Let's take particle or molecules. Okay. So suppose we have 3 particles, and each of the particles has spin half. Okay. kept into homogeneous magnetic field. Magnetic field V at temperature T. Okay. Now we have to find out what is the possible microstep and corresponding probability. The question is, what are the corresponding microstates and their probability? So the problem is like these particles are spin half particles. The spin half particles is like that. When you put a spin half particle in a magnetic field, what will happen? It either the spin of the particle either showing up or it can show down. Okay. So this is the property. So in this case the spin is plus half, and in this case the spin is minus half. Okay. These are the two possible combinations that each of the particles can show. So based upon that, we will consider the all possible configuration for this particular three particle system, and you also calculate the corresponding weight of each of this configuration and the probability, just like we did in the previous example. Okay. So the configurations, the weight of microstates and the probability. So in the first case, what can happen is that all of the three particles are in spin up, like up state. Okay, so all are in up. So all particles is up, up, up. Okay. And yeah, the total number of combination here also like 2 to the power 3, right? So there are two states are possible, and total number of particles is 3. So total number of combination can be happen 2 to the power 3, that is 8. Just like the previous example, it was 2 to the power 4, it is 16. Here there are 3 particles, so in this case it will be 2 to the power 3, indistinguishable particles, obviously. Yeah, these 3 particles are indistinguishable. Sorry, distinguishable. No, distinguishable. Distinguishable. Okay. That is a key assumption. Okay. So now all are in up, and let's suppose this is the one configuration. For this configuration, all microstates can happen, and the probability would be 1 by 8, since the weight is just 1. And second case, what can happen? 2 are up and 1 is down, right? This is also configuration where 2 spins can be upstate and 1 spin can be downstate. So the possible configuration are like this: first 2 are up, last one is down, or the first and last one are up, the middle one is down, or the first one is down and the last 2 are up. So these 3 possible combination can happen for this configuration. So the weight is 3 and the probability is 3 by 8. Okay. And second is 1 is the opposite of the previous one. 1 is up and 2 is down. Okay. For this particular case, the combination would be first 2 are down, last one is up. First one is up, last 2 are down, and the middle one is up, the first and last are down. These are the 3 combinations. Here also 3 by 8, and last is all 3 are down, right? All 3 are down. So here it will be down, down, down. The combination, the probability will be 1 by 8, right? So This is the microstate, and this is the configuration. Similar way, just the way we did in the previous example. Similar way to find out the possible combination for each of the configuration, and from there you can calculate the probability of this of the each configurations. Now using this quantity, using all this information, you can calculate many statistical quantities, right? One can be the average of this whole this whole structure, right? Like the average spin, right? So in the first case, let's suppose there is a spin, total spin would be 3 particles and spin up state. So there will be some spin, total spin into the probability S1 into 1 by 8. Similar way, S2 into 3 by 8, S3 into 3 by 8, and S4 into 1 by 8. Okay. So in this way, by using the probability total number of spin value of each of the configuration, you can calculate the average spin of the system also. In this way, this calculating all these microstates, macrostates, probability, basically in the long run, you can use this information to calculate the thermodynamics, many kind of thermodynamics property of a system. Okay. So now we'll start. We have discussed the weight. Okay, so weight is this formula, right? This is the formula for the weight. So the formula looks like this. W is basically n factorial, n 0 factorial, n 1 factorial, n 2 factorial, over. So it's like the number of way n0, n1, n2 particles are distributed. And these are we termed it as the weight of the distribution. Okay. Now we'll find out that what is the like by what is the distribution, particular distribution that ensures that uh, the maximum possible the distribution that maximize this W basically, because the maximum W, as you can see, in the maximum W, the probability of that particular system can attain that configuration would be the highest. Okay, like here you can see in this previous problems also you can see where the weight is maximum, like here the weight is 6. The probability of the system that take that particular distribution is 6 by 16. That is the maximum, right? So to find out, in order to find out where the system would end up, we have to find out where this particular weight is getting maximized. For what particular for what particular distribution this weight is going to maximize. That we want to find out. Okay. So we want to find out our distribution for which this weight W is going to be maximized. Okay. Okay. So this is our primary goal. Okay. So since we know this W is this number of molecules are very high, and if you calculate their possible combination, that would be a very high number. Okay, so it's better to work with the logarithmic of that particular number. Okay, so for the sake of calculation, what we will do, we will take the log ln W, ln of factorial by n0 factorial, n1 factorial, n2 factorial, like that. We can then write this like this. Ln of n factorial minus ln of n0 factorial plus ln of n1 factorial plus dot 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 like this. Now since n is very large number, so we can use this thing called Stirling approximation. So we'll write it like this. This is Stirling approximation. N into ln n minus n0 into ln n0 plus n1 into ln n1 like this. You can write it in the summation form. N into ln n minus summation over I in I into ln of n. So this is the functional form of ln W. Okay. And also there are also the two restrictions. We have to also consider the restriction of the system. That is the first restriction that we have calculated, or constraint you can say. It is the total number of energy of the system is sum of the individual energies, right? So if let's suppose n0 numbers of particles are in E0, n1 numbers of particles are in E1, n2 numbers of particles in E2, so like that. If you distribute it, the total number of energy, let's suppose E, so that would be summation of each of the individual energy levels. That is, so energy level, ground state energy level has total energy n0 into E0 plus n1 into E1 plus all the summations. And the second constraint is the total number of particles is also constant. So n is total number of particles, that is a summation of summation of the particles in the sub levels. Okay, n0 plus n1, so like that. Okay, so now we know. To find out where this distribution, for what particular distribution this ln W is get maximized. For that we know we have to take the derivative of this ln W, right? And so for a particular distribution, this derivative of ln W will be equal to 0. So that is the particular distribution where this weight is getting maximized. Okay, that is simple calculus that we all know, right? So maximize this by evaluating d of ln W equal to 0. Okay. Now from basic calculus course, you know, if suppose a variable y or f is function of x and y, if you take a total derivative of x, it would be del f by del x into dx plus del f by del y into dy. Right, this is how you write a total derivative. Here you are writing the total derivative of a ln W, right? And like here f is a function of x and y, so because of that you can write it like this. Now here ln W is a function of all this thing, n1, n0, n2, all of this thing. So you can write this total derivative as a sum of this partial derivative. So by using this rule, so you can write it like this: I equal to delta of ln W into delta of ni, partial derivative basically, into dni, like the way we have written here. Okay. And also you have to write this constraint also in the integral form. So first constraint we will have to write it like this. If you take the integral form, so if you take the derivative in both the sides, so d of e, since e is constant, so d of e will be equal to 0. So it will now become di into d of ni equal to 0. Since d is equal to 0, the e is constant. Similar way, the second, the differential form of the second constant would be d of ni summation over I equal to 0. Since n is also constant here, so if you take g of n, it will be equal to 0. These are the two constraints. This is the thing that we want to maximize. So to do that, since it's not a normal like thing that where you just have to calculate the derivative equal to 0, and from there you get the maximum distribution. Here you have to also consider the constraint. So to incorporate the constraint to the main equation, here what we will be going to use is that is known as the Lagrange method of undetermined multiplier. Okay, where you have to maximize this distribution by also considering the constraint into the equation. Okay, so if you consider that, so in order to write it like that, so first we will have to write this. So d of ln w that we want to maximize, this thing you have to write it like this. First is the partial derivative summation, and now also you have to consider the constraint. Okay, first is this gni, and second is this epsilon I into gni, and this thing you have to equate it equal to 0. Now, in the method of Lagrange undetermined multiplier, you have to multiply this to constraint with a particular coefficient or multiplier. Okay. So first is the alpha. Second thing we are multiplying is minus beta. Okay. So these are the undetermined multipliers. So first task will be to find out the expression of this undetermined multiplier. There are values of basically the alpha and betas. So now the next step, what we will do, we'll take the summation outside, the summation of I delta of ln w plus delta ni plus alpha plus beta epsilon I into g of ni equal to 0. Okay. So this is the particular, so this thing we have to, so now this thing, so in the summation, inside the summation, we can write it like this. So maximizing this thing is equivalent to maximizing this thing. Delta of ln w of delta ni plus alpha minus beta epsilon I equal to 0. So this is the equation you get. Now we know that ln w is basically n into ln of n minus summation over I ni into ln ni. Now we have to take the derivative of it. So since we want to calculate this thing delta of ln w with respect derivative of ln w with respect to ni, so that thing we have to find its analytical expression first. So to do that, what we do, we will first take the derivative of delta of ln w of delta of ni is basically equal to delta of ni into n ln n ln n minus delta of ni into summation of ni into ln ni. These are the two quantities you have to first calculate. So first we will start from this first quantity, okay. So if you do the derivative, it will looks like this. N into n by n into delta n by L delta ni. If you take the derivative with of ln n with respect to ni, you will get this plus ln n into delta n by delta ni. Now here, from here you can take the n plus the del n into del ni as common. So then it will be reduced to del n by del ni. Okay. And del n by del ni is nothing but equal to 1. Okay. So this would be equal to 1 plus log 1. Okay. Now the next thing that we want to calculate is this part. This part, if you calculate, it would be like this. Delta ni is I or j, let's suppose, just to avoid any complication with the sign. So let's use the index as j, nj into ln nj. So if we do the derivative, it would be summation over j. Let's take the summation outside, del n I into nj into ln nj. Now if you take the summation, it will be summation over j nj by nj into delta nj by delta ni plus ln of nj into delta nj into delta ni. Now here it will be summation over j 1 plus ln nj into delta nj plus delta ni. Now from here it will be summation, so nj by ni equal, this would be equal to 1. So now it would be summation over j, so all possible j, so it will become 1 plus ln of ni. Okay. Okay, so we have got the quantity, so now we have to write it. Okay, so now we have to write it like this. So our main thing is like this. So delta of ln w by delta ni plus alpha minus beta epsilon I equal to 0. Yeah. So now from here we have to do the derivatives. So if you substitute those derivatives, you will get 1 plus ln n minus 1 minus ln ni plus alpha minus beta ei equal to 0. Now from here it will be ln of ni by n plus alpha minus beta epsilon I equal to 0. Now from here uh, you can place this part on the right hand side. So now it will become ln of ni by n equal to alpha minus beta epsilon I. So from here ni by n equal to e to the power alpha minus beta ei. Okay. So now from e to the power alpha into e to the power minus beta ei. So now we have to find out what is the expression of alpha and beta. To get the expression of alpha, it's quite easy. You have to first summation over all the particle numbers. So ni we know is n into to the power alpha into to the power minus beta, right? Take the summation on both the sides on I. Now from doing that you will get n equal to n into to the power alpha into e to the power beta E. So e to the power alpha will now become 1 by summation over I into e to the power beta E. Okay. This is the expression of the e to the power alpha thing. So if you put it here, now it will become Ni by n into equal to e to the power e to the power beta ei divided by summation over e to the power minus beta ei. Okay. And here beta is nothing by the inverse of the temperature 1 by kBT. Okay. So this is the particular distribution, as you can see. So this particular distribution is known as the Boltzmann distribution. Okay. Boltzmann. So this particular distribution is known as the Boltzmann distribution. So that means that we have started with the discussion is that let's suppose we have n total n number of particles. How the particles are distributed in each of the energy state E0, N0, E1, N1, E2, N3, N2. So like that, how the by which distribution the particle should follow to fill up all this energy state in order to get the maximum weight. So weight that we have defined as W. So our goal has to find out that particular distribution which maximize this weight. And so that means that that particular weight, so if that particular distribution gives the weight the maximum thing, that means that the system will basically attain that particular weight, right? If that particular weight has the highest probability. So this distribution is basically given by this. So that means N0 particle will be the N0 I mean the distribution at the E0 energy level is basically given by N0 equal to n into e to the power minus beta E0 divided by the whole summation. Okay. Similarly, the N1 would be n into e to the power beta E1 divided by this whole summation. Okay. So this is how, that means each of the particles are the populations are distributed in each of the energy levels, okay, using this Boltzmann distribution to maximize the weight. So yeah. Okay. Okay, so now our next objective is to get the to extract out basically the informations, most amount of information from this particular distribution in order to know the statistical properties of the system. Okay. So let me write this distribution again. So Ni by n is equal to e to the power minus beta I by summation over e to the power minus beta I. Summation over output. So this particular quantity that is in a denominator, this thing we are giving it as a name, which is known as the partition function of the system, which is a very relevant quantity in the statistical mechanics, especially if you calculate the partition function of any thermodynamic system. By using that thing, you can basically calculate all kind of thermodynamic measurements. You can do any kind of thermodynamic measurements if the system is in equilibrium, obviously, by using this partition function. So this is a very important quantity for the definition of a thermodynamic system. So this is known as the partition function. So we are calling is at Q. In some places they are calling it as Z also. So yeah, so Q, the partition function, is basically the summation over all the energy state into t to the power beta EI. So it would be like this. So e to the power minus beta E0 plus e to the power minus beta E1 plus e to the power minus beta E2. Like this, if you E0 has 0 energy state, then it will become 1 plus e to the power minus beta E1 plus e to the power minus beta E2, like this. This is how the partition function of very simple system, but the particles are just distributed in the energy states, looks like. And also we can consider degeneracy. Okay, let's suppose two states that are two different states but having same energy values. Okay, so that means that that energy is doubly degenerated. Okay, so so a particular energy value is shared between two different states. Okay, so in that case you can consider that degeneracy also into this expression of the partition function. So if you consider the degeneracy, the expression will be changed a bit. So the expression will become like this. So summation over I Gi into e to the power minus beta EI. So Gi is the basically the degeneracy associated with the energy level EI. Okay. So this thing you can write it like this. So let's suppose first energy level has degeneracy G0, so G0 plus G1 into e to the power minus beta E1 plus G2 into e to the power minus beta E2. So like this way you can write the total partition function of this system, right? And here beta is nothing but 1 by KBT. 1 by KBT. Yeah. Also, for the sake of calculation, you can write this Ni by n is basically termed as the population of each state. You can write it this Ni by n as the Pi, that is known as population of the ith state. This is the in general terminology that we use in the context of statistical mechanics. The population basically is the number of fraction of particles that basically occupying that particular energy state. So that thing we termed it as the population of that particular state. Okay. So Pi is then, that means e to the power minus beta Ei by Q. So this means for, let's suppose these energy states are there. So for this system, if you calculate the partition function Q, and if you calculate the energy, if you calculate the energy of the state that you are want to calculate the population. So if you calculate these two quantities, so by using that and by plugging those values into this particular formula, you can get the population or the fraction of the particles that is occupying that particular energy state. So this is the basically the formula, the main formula that we are going to use throughout this first lesson, or in the future lessons also. This is a very important quantity. Yeah. Okay. So now we'll first discuss like what is the effect of temperature into the system. That we want to first calculate. Okay. So let's now find out the significance of partition function by considering how it depends on temperature. Partition function expression is equal to Q equal to summation over J Gj into e to the power minus beta Ej. So you can write it like this. If let's suppose E0 energy has value 0, so it's a ground state. E1, E2, like this, all the states are there. And let's suppose each state has some degeneracy. Suppose E0 states have, let's suppose G0 has the degeneracy, E1 state has G1 degeneracy, E2 state has G2 degeneracy. So like that way, every state, let's suppose, has some associated with some degeneracy. So in that case, the Q would be G0 into e to the power minus beta E0 plus G1 into e to the power minus beta E1 plus G2 into e to the power minus beta E2 plus dot dot dot. And if you consider the ground state energy as E0, so this would be equal to 1. So it would be G0 plus G1 into e to the power minus E1 by kBT. Since you are considering the temperature, let's write this expression in terms of temperature for the benefit by E2 by kBT plus dot dot dot. So now, so first take the, so we consider the extreme end of the temperature. So first we consider where the temperature will be tends to 0, and next case we will be consider the temperature tends to infinite. Okay, very high temperature. So okay. So let's first consider the case where the temperature is T tends to 0. So if T tends to 0, this factor part e to the power minus E by kBT, this would be becomes e to the power minus E by kB into 0, right? So that means it will tends to e to the power minus infinite. So e to the power minus 1 by e to the power infinite. So that would be tends to 0, right? So if you consider this thing equal to 0, so that means every energy value, like e to the power minus C1 by kBt is also tends to 0. E to the power minus E2 by kBt also tends to 0. So likewise, every other factors of this associated this Boltzmann factors, you can say this. These are basically known as the Boltzmann factors. So these all these Boltzmann factors associated with each of the energy levels are basically tends to 0, right? So that means the Q would be G0 plus G1 into 0 plus G2 into 0 plus dot dot dot. So Q would be G0. Okay. Yeah. And yeah, so this would happen. And yeah, so the partition function is only given by the partition function is only given by the degeneracy of the of the ground state, right? And if you consider the population of this different state ni by n equal to e to the power minus beta ei by q or ti. So what will happen is that so this will become e to the power minus beta ei. Yeah. So this so yeah. So now for n0 at I equal to 0, let's consider n0 would be equal to n0 by n into e to the power minus beta into 0 into q. So that would be n0 by n by q. Okay. And if you consider other states, let's suppose I equal to 1. So in that case, n0 would be n1 would be by n into e to the power minus beta by e1 by q. Now since here t tends to 0, so we know this thing is this Boltzmann factor will be tends to also 0. So n1 by n is equal to basically 0. So n1 will be equal to 0. So similar way, if you calculate for I equal to 2, similarly you get n2 will be n2 by n equal to 0. So n2 will be also equal to 0. So as you can see, that means what happens is that at this absolute 0 temperature, where basically T tends to 0, T tends to 0 phase. What is basically happening is that all the particles can see this n0 number of n0 that is the number of particles at ground state has the total number of particles. Okay. If you consider degeneracy equal to 1, this n0 is basically equal to n. So that means all the particles at T tends to absolute value temperature, all the particles basically boils down to the ground state of the system. Okay. So that means in this T equal to 10, T equal to 0 configuration, all the particles in numbers of particles n0 equal to n comes to this ground state. Okay, 0 equal to 0. And higher energy states E1, E2, E3 doesn't contain any particles at all. Okay. So this is one of the and also experimentally it also has been shown out like that if you cool the system at very low temperature, close to 0 temperature, so it has been found out that all the molecules of the energy level goes to the ground state of the system. Okay. So this theoretically also here also you can see the same thing is happening. So in that way, basically the experiments basically gives a validation of this theory or this expression. Yeah. So next thing, so we checked what happens at t tends to 0 case. Now we have to consider what happens at t tends to infinite. So t tends to infinite. Let's go. Okay, so T tends to infinite. Okay, T tends to infinite. So our expression was G equal to, sorry, Q equal to G0 plus G1 into the power minus epsilon 1 by KBT plus G2 epsilon 2 by KBT. So like that. So now T tends to infinite, what will happen? Q will be G0 plus G1 into to the power epsilon 1 by EB into by infinite. So what will happen is that if you take this A into infinite, so 1 by infinite is basically tends to 0, right? Tends to 0, 4 to the power minus 0. So this tends to basically 1. Okay, so that means C to the power minus epsilon 1 by kBT, this tends to 1, epsilon 2 by kBT, this tends to 1, sorry, tends to 1, sorry, tends to 1, tends to 1, so like this. So every of this Boltzmann factor will be tends to 1 for the case of temperature tends to infinite. So in that case, you would be equal to G0 plus G1 into 1 plus G2 into 1 dot. C2 would be equal to G0 plus G1 plus G2 dot. So basically, so this thing is basically the summation over all the degeneracies, the number of all the degeneracies of the system. Okay, so now if we see what will happen is that is the population. So at T, so you see at T equal to 0, all the particles are basically boils down to the ground state of the system. Now what happens if you raise the temperature to very high value, it tends to infinite. So in that case, if you consider the population expression Pi equal to Ni by N is equal to e to the power minus beta epsilon I by the partition function Q. Here partition function is fixed, that is this thing, e to the power minus beta Ei by G0 plus G1 plus it's like this. Oh, it's not it for sake of understanding, write it as kBT. Now, if you make the temperature very high, you know this epsilon I by kBT, this thing will be tends to 1. Okay, so that means Pi equal to Ni by N will be equal to 1 by this Q. So the population of each energy state is basically N by Q. Okay. So that means it doesn't matter whatever the energy values are in each state. Previously, in general, in normal state, at a normal finite temperature, Ni is basically N into e to the power minus beta epsilon I by Q, right? So that means this Ni thing, the expression of Ni is dependent upon the energy of that particular distribution. Okay. So the energy of that particular state basically decide what is the number of population that I can occupy. Okay, but if you take the system temperature at a very high value, T tends to infinite, here T is finite. Okay, if you take T equal tends to infinite, here you can see the population of each of the states are basically independent of the energy. Okay, so every state has a equal number of energy, equal number of population. So each state starting from E0, E1, E2, E3. So each of the state will have N by Q, N by Q, N by Q, N by Q, like this population. Okay. So this is the way, as you can see, the system will behave in the two extreme cases of temperature. So in summary, what we can say is that in T tends to 0. So what you can see in summary, what happens at t tends to 0, its partition function q will be equal to g0, and all the particles are populated in the ground state of the system. Okay. So this thing will be happen for the case when the temperature will be tends to 0. Physically happens in the system. Okay. Next thing is at t tends to infinite, you can see calculated g would be the summation of all the all of the, you can say, degeneracies, g0 plus g1 plus g2, and we have find out the population is basically n by q. That means every energy state EI has equal population, and it doesn't depend on the energy of that particular energy, that means EI, of that particular ith state. Okay. So this is in summary what will be happens inside the system in extreme temperature cases. Okay, now next we'll discuss some problems on this thing. Okay. So the problem one, the first problem. The first problem is we have two energy levels. Okay. So one has energy E1 equal to 0 and second level is E2 equal to E. So these are the two energy levels. Now we have to find out the population of each of the energy level and what will happen at the case for t tends to 0 and t tends to infinite. Okay. So basically, two energy levels are there, 0 and E, two energy level system. So first we have to get a general expression of the population of each of the energy level, and after getting that expression, we have to calculate for both the cases where t tends to 0 and t tends to infinite, what happens to that particular system. Okay. So let me just write out. So these are the energy level. One is having energy E, second is having energy 0. So the first, so this problem. So to solve any this kind of problem, the first thing, any this kind of system, like whether it's a two-level system, three-level system, two-level four particles, two-level, three-level five particle system, whatever the system is, the first thing, the first and most important thing that we should calculate is the partition function of the system. Okay. So for this system, it's quite easy. Just Q is, we know, is summation over I to the minus 1 of beta EI. That is the general expression of the partition function. Here, this just two energy levels are there. So the summation over will be 2 e to the minus beta E1 plus e to the minus 1 of beta E2. So E1 is 0, E2 is E. So it will be 1 e to the minus beta into 0 plus e to the minus beta E beta into G. So it will become 1 plus e to the minus minus beta E. So that is the partition function Q. Okay. So since you got the Q, now from this we can calculate the population. So population formula, you know, EI is basically Ni by N. Population, you know, is nothing but the fraction of total particle that is occupy in that particular state of interest, our, that is the ith state. So EI is basically Ni by N, which is e to the power beta EI by Q, right? So for the first energy level P1 would be N1 by N, that is basically e to the power minus beta into 0 by Q is 1 plus e to the power minus beta E. So that would be so this is name is as P0 since it's the ground state or 0th state. Okay. So P0 is basically 1 plus 1 by 1 plus e to the power minus beta. Okay. So this is the population at 0th state. Okay. Population at ground or 0th state. And P1 is the population at first excited state. Population at first excited state, that is given by N1 by N, N1 by N. So N1 by N is given as Q. So this will give you e to the power minus beta E by 1 plus e to the power minus beta E. Right. This is the population of the first excited state. Okay. So we got your answer, right? So P is for P0, this is the value. For P1, this is the value. So this was the answer of the first part of the problem. The second part of the problem, it has been asked, what will happen for the case at t tends to 0 and t tends to infinite. Okay. So for t tends to 0, we know e to the power minus e by kbt. So this t tends to 0, so this will be this into 0, right? So e to the power minus infinite, this tends to 0, right? So this tends to 0. So that means P0 would be e to the power minus, sorry, P0 is 1 plus 1 by 1 plus e to the power e. So since at t tends to 0, at t tends to 0, this thing tends to 0, right? So which means p0 would be 1. Okay. So that means, as we have discussed in the previous case also, so at t tends to 0, so population is 1. So basically, that means n0 is equal to n. So all the particles basically occupies in the ground state of the system. That we already know in the previous discussion that certainly will happen if the system temperature tends to 0. Now the next case is as t at t tends to infinite. Okay. So that in that case also what will happen, you already shown that, but still let's verify here also. So at t tends to infinite, what will happen? E to the power minus beta a into infinite. So this tends to e to the power minus 0. That means tends to 1, right? So in that means, so p0 would be become 1 by 1 plus 1. So that means 1 by 2, 0.5. Similarly, p1 would be also 1 by 1 plus 1, because e to the power, so beta is also there. So since t tends to 0, so that means this term also here tends to 1. So this would be also 1 by 1 plus 1. So it will also become 1 by 2, 0.5. As you can see, so the population of zeroth state, ground state, n0 is 0.5 of n, and population at the first excited state, that is n1, is 0.5 into. So you can see the particles is basically equally distributed in both the levels. That we have also predicted from our earlier discussion what will happen at t tends to infinite. So same things happens here also. Both the states getting equal number of particles. Okay. So yeah, so this is the problem. Now we go to another problem. Second problem. System consists of three independent particles localized in space. Localized in space. Each particle have two states of energy, 0 and E. When the system is in thermal equilibrium with a heat path at temperature T, calculate the partition function. Okay. So this is a very generic problem. So there are two energy states are there. One is having zeroth state, ground state with energy 0, and one is the first excited state which is having energy. Now, so here there are three particles are there, okay, independent particles. So we basically mark each of the particles. So like A, B, C, like that. Okay. So we have to first consider what are the possible ways the particles can arrange in these three energy states. And you also have to calculate the energy of each of the particular configuration. And okay, and from there also, from the arrangement of that configuration, we can also calculate the probability of that particular configuration also. Okay. So here, so this is one method. There is also another method. So this method that we have discussed. It's a pretty much long method. Here you have to write all the combination and all. But first we'll try this method only because it's easier to understand. And then next, I'll also be telling a second method where in solving problems, by using that method, you can easily solve this kind of problem very easily. So, but that method I'll discuss next week. Okay. So. Yeah, so let's mark the particles. Since the particles are all independent, so let's first mark the particle at A, B, and C. So, yeah. So there are two states. One is having energy E, second is having energy 0. So first write the configuration. Second write the energy state. Next write the total energy. Okay. And also you can write the degeneracy of the system. So first case is the case 1. So where all particles are in, let's suppose in ground state. Okay. This one is all particles are in ground zero state. In this case, that means 0 and E two energy states are there. So all the particles A, B, C are in 0 state. Okay. No particles are in. No particles are in energy state E, so that means the total energy would be 0. And only one way this degeneracy can occur. So total energy is 0, and the number of way this thing is possible is 1. So degeneracy will be 1. Next is the two state in E and one state in 0. Okay. So this will happen like this. So let's suppose two state in E. So AB can two state can be E. So AB is in E. AB is in, sorry, two state can be E and one state can be 0. Okay. So two state can be, so AB let's suppose is in E and C is in 0. Another case where CA is E and B is in 0. Another is BC in E and A is in 0. So in this case, the energy for all of this configuration here is 2E, here is also 2E, and here is also 2E. As you can see, although these three types of configuration are different, but since they share the same energy level, so this can be counted as a degeneracy. So for this particular energy of the system 2E, has 3 degeneracy. Next is the opposite case. So 2 state in 0 and 1 state in E. So that is the opposite of it. So AB is in 0, C is in E, CA is in 0, B is in E, and BC is in 0, A is in E. So here also the energies are E, E, and E. Okay. So here also the degeneracy is 3, since 3 types of uh, combination share the same energy. So so the degeneracy is 3. The last one is all are in E. So all the energies are in E, A, B, C, and no particles are in 0 state. So in this case, the total energy would be 3E, right? And the number of degeneracy would be 1. Okay. So we got all possible combination, all possible configuration, all possible combination by which this configuration can happen. We calculated the energy associated with each of the configuration, and the corresponding the degeneracy is also calculated. So we have all the tools that are needed, all the values basically that are needed to calculate the partition function of the system, right? So the partition function we know is the expression is this. So capital, so that let's write it as capital 2. Now capital 2 is equal to summation over I gi into e to the power minus beta ei. Okay. So here so there are 4 states we know. So G1, so there are 4 configuration is there. So summation into 1 from 1 to 4, right? So the summation will be like this: G1 into e to the power minus b E1. First let's suppose G0. G0 into e to the power beta E0, and G1 into e to the power minus beta E1, G2 into e to the power beta E2, and G3 is equal to e to the power minus beta E3. Okay. So here E0 is the first case where E0 is the first energy of the first case. This is basically E0, where all the particles are in ground state. Okay. So that means E0 is basically 0. Second case, and G1 is G0 is equal to 1, since the degeneracy is 1. And in the second case, where 2 states are in E and 1 state is at 0, so in that case there are the energy of the system for that case is 2E. Okay. So E1 is 2E, and G1, the degeneracy for that particular state is basically 3. This is the second case. The third case is the 2 states are in 0 and 1 state is in E. So the E2 is basically E in that case, and the G2 is basically 3. Okay. The G2 is basically 3. So this is the configuration for this case. And the last case, E3 is basically where all the states are in the energy state, first energy state. In that case, the E3 is basically 3E, and G3 is basically 1. Okay. So just put all these values in the expression of the partition function. So it will give you 1 into e to the power minus beta into 0 plus 3 into e to the power minus beta 2e plus 3 into e to the power minus beta e plus 1 into e to the power minus beta 3e. Okay. So if you do that, you get 1 plus 3 into the power minus 2 beta e plus 3 into the power minus b. Sorry, it's minus 2 beta e plus e to the power minus 3 beta e. This is the partition function for the whole system. Okay. So this is one of the way You can calculate the partition function of this three-level system having two energy states. There is another method which is a very fast method. By using that also you can calculate. That method is like this. So this is for three particles, right? So just write it as Q3. Okay. This is method one. Okay. Method one. There is also second method two, by using which also you can calculate. Okay. The second way is like that. So first calculate the partition function for a single particle system. A single particle, you know, is Q1 is nothing but epsilon into 1 plus beta E, summation over I, to the power minus beta EI. Single particle, either it can happen, either it can take ground state or it can take the first excited state. So 1 e to the power minus beta into 0 or e to the power minus beta into E. So that would be 1 plus e to the power minus beta E. So that is the partition function for a single particle system for a two level case. Okay. Now for three particle system, what you have to do, Q3 is nothing but just basically takes the power of that number of particles with the Q1 to the power cube. Okay. Since there are three particles, so Q1 to the power cube. So if there are n particles, Qn would be in that case Q1 to the power n. Okay. So now if you do the Q1 plus e to the power beta n to the power q, if you do that, you'll be getting the same expression that you get in by using the first method. 1 plus e to the power minus 3 beta e plus 3 into the power minus 2 beta e plus 3 into the power minus beta e. The formula of q of x plus y cube formula. Yeah. So similarly for q, if there are n particles, and let's suppose there are more energy levels are there. Okay, so it would be like this: 1 plus e to the power minus beta e1, 1 plus e to the power minus beta e2, dot 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 to the power n. Let's suppose there are there are many numbers of levels are there. There are n numbers of particles are there. So in that case, this would be the general formula to find out the partition function from the system, provided that the system, the particle should be indistinguishable. Okay. Independent particles. The particle should be independent particles. So there, for that case only, this formula will be correct. Now we'll do some problem. Some two more problems. System with four from degenerate equally spaced energy levels E0, E1, E2, E3. What is the population probability of the lowest energy level at t tends to infinite and t tends to 0. So, sorry, t tends to infinite. The options are option A is 0.25, option B is 0.0, option C is 0.75, and option D is 1. So as we have discussed earlier, what happens at t tends to infinite? So we know when T temperature tends to infinite, what happens is that the Boltzmann factor to the power minus E by kBT. This factor, since T this E to the power by kBT, if T tends to infinite, this thing tends to 0. So because of that, this thing E to the power minus 0 tends to 1. Okay. So, and we have discussed. So this means what happens is that if this factor is tends to 1, this means all energy levels are equally likely to be occupied. Okay. So that means there is no energetic differences. Energetic preferences. Okay. There is no energetic preference. So that means since there are 4 number of energy states are there, so that means each number of energy states, so the probability of finding a particle in any specific state will be equal to 1 by 4. That means it will be equal to 0.25. Okay. So that means the correct answer is the option, right? So so each of the population gets the equal probability to be gets filled. Okay. So similarly, if instead of t tends to infinite, if in the problem it was given at t tends to 0, we know that t tends to 0. What will happen? This Boltzmann factor, sorry, E by kBT. This Boltzmann factor tends to 0. In that case, all the particles comes to the ground state. So only the probability at particle being in ground state would be maximum, right? It will be equal to 1, and the other state will become 0, right? So this is it. So that's it for today's class. Okay, so we have discussed the theories and also discussed some numerical problems. If you don't have any question, then we can end the class. Okay, then I'm going to end the class.